Welcome to Astro Odyssey. Explore the universe. But as something far wilder an ocean of motion, where countless unseen worlds drift in silence? In this vast cosmic sea, there are planets that belong to no star. Worlds untethered from any source of daylight, warmth, or familiar rhythm. They travel alone through interstellar space, carrying with them the history of violent beginnings and ancient separations. These are rogue planets, sometimes called orphan worlds. And their existence forces us to confront a reality that feels almost unsettling. The galaxy may be filled with far more lonely planets than stars themselves. They do not shine. They do not announce themselves. And yet they may be everywhere. Gliding between star systems like ghosts of planetary systems long forgotten. For most of human history, planets were defined by their relationship to a star. Even our language reflects this assumption world's orbit. Stars, host, and planetary systems behave like orderly families. Our solar system reinforced that idea. A model of relative stability where planets follow elegant paths around the sun like dancers in a cosmic performance. But nature, it turns out, is rarely that polite. As astronomers began discovering planets beyond our solar system, they quickly realized that chaos, not order, may be the rule. Systems packed with massive worlds on unstable paths, stars born in crowded clusters, and gravitational interactions. Violent enough to tear planets from their homes, all pointed toward an uncomfortable conclusion. Planets don't always stay where they're born. The idea of rogue planets was once almost philosophical, a thought experiment more than an observable reality. Scientists speculated about their existence, but without direct evidence, they remained on the fringe of planetary science. That began to change as technology caught up with imagination. Advanced observatories and space-based telescopes started revealing subtle clues. Tiny distortions in light that hinted at massive objects moving invisibly between the stars. These were not stars, not brown dwarfs, and not debris. They were worlds' planetary mass objects, wandering freely through the Milky Way. Each detection added weight to a startling possibility. These cosmic nomads are not rare accidents, but a fundamental population of the galaxy. Recent observations suggest that rogue planets could number in the billions or even trillions within our galaxy alone. Some estimates propose that for every star in the Milky Way, there may be at least one free-floating planet, and possibly many more. If that's true, then the majority of planets in our galaxy may never see a sunrise. They drift through perpetual night, their surfaces frozen solid, their skies black and starless. And yet, despite their darkness, they are not empty or meaningless. Each one represents a complex history of formation, motion, and survival, shaped by forces that operate on scales almost impossible to fully comprehend. What makes rogue planets especially haunting is their invisibility. Unlike stars, they do not generate their own light. Unlike orbiting planets, they do not reflect the glow of a nearby sun. They move silently through space, detectable only when they briefly betray themselves by bending the light of a distant star, or subtly influencing the motion of nearby objects. This means that for every rogue planet we detect, there may be thousands more passing unnoticed, slipping between star systems like shadows. The galaxy we see, illuminated by stars and nebulae, may be only a thin veneer over a much larger, darker structure dominated by unseen worlds. And this realization changes something fundamental about how we see the universe. It suggests that planetary existence is not dependent on warmth, light, or stability. Worlds can form, evolve, and persist even after being violently cast away from their stars. Rogue planets are evidence that the cosmos is not just a place of creation, but of exile and survival. They invite us to rethink what it means for a planet to exist at all, and whether the conditions we consider normal are actually the exception rather than the rule. In the cold, dark spaces between the stars, an entirely different kind of planetary story may be unfolding. To understand how a planet becomes a rogue, we have to rewind to the earliest moments of planetary birth. When solar systems are anything but stable, young stars are surrounded by swirling disks of gas and dust. Chaotic environments where worlds take shape amid turbulence and violence. In these newborn systems, planets do not glide gently into their final orbits. They migrate, collide, and tug relentlessly on one another through gravity. Massive gas giants form quickly, and once they do, they become bullies reshaping entire systems with their gravitational dominance. In this early cosmic adolescence, stability is fragile, and exile is a very real possibility. One of the most widely accepted explanations for rogue planets is gravitational ejection. Imagine a tightly packed planetary system where several massive worlds orbit close together. Over time, small instabilities grow. A near miss between two planets can drastically alter their paths, sending one inward, toward the star, and flinging the other outward. If the timing and angles are just right or wrong, a planet can gain enough velocity to escape its star's gravitational grip entirely. In that instant, a world that may have spent millions of years circling a sun is violently cast into interstellar space, never to return. The analogy often used by astronomers is cosmic billiards, but the reality is far more dramatic. These are not gentle nudges, but gravitational slingshots, involving energies that dwarf anything humans can produce. A single close encounter with a gas giant several times the mass of Jupiter can permanently alter a planet's fate. And these encounters are not rare. Observations of exoplanetary systems show that many are packed far more tightly than our own solar system ever was. Chaos, it seems, is common. Ejection may not be an exception. It may be a natural outcome of planetary formation. Stars themselves also play a role in creating rogue planets. Most stars are born in clusters, emerging from massive clouds alongside hundreds or even thousands of siblings. In these crowded stellar nurseries, close stellar flybys are inevitable. When another star passes near a young planetary system, its gravity can disrupt planetary orbits, destabilizing entire systems in a single encounter. Some planets are captured by the passing star, becoming strangers in a new system. Others are flung away entirely, severed from both stars, condemned to wander alone through the galaxy. But ejection is not the only path to becoming a rogue. There is a more mysterious possibility, one that challenges the very definition of what a planet is. Some rogue planets may never have orbited a star at all. Instead, they may form directly in interstellar space, born from collapsing clouds of gas that are too small to ignite nuclear fusion. These objects blur the line between planets and stars, forming in isolation like failed suns. They emerge cold, dark, and solitary from the beginning, never knowing the warmth of starlight or the structure of a planetary system. This idea unsettles traditional classifications. If a planet can form without a star, then what truly defines it? Mass alone? Composition? Origin? Rogue planets force scientists to confront these questions because they exist in the gray areas of cosmic taxonomy. Some may be indistinguishable from gas giants ejected from systems, while others may be rocky, Earth-mass worlds that condensed quietly in the depths of molecular clouds. The galaxy may be producing planets through more than one mechanism, each leaving behind worlds with radically different histories but the same lonely fate. What's even more remarkable is that many rogue planets are not small. Some are as massive as Jupiter or larger, capable of retaining thick atmospheres and generating internal heat for billions of years. Others may be rocky super-Earths, dense and geologically active long after their ejection. These worlds are not dead debris. They are fully formed planets, complex and dynamic, carrying the scars of violent beginnings. Each one is a survivor of cosmic upheaval, proof that planetary existence does not require a peaceful origin. In this way, rogue planets become storytellers of chaos. They are evidence that planetary systems are not delicate clockworks but turbulent arenas shaped by conflict, chance, and loss. Every orphan world drifting through the galaxy is a reminder that creation and destruction are inseparable in the cosmos. Worlds are born not only to orbit and endure, but sometimes to be expelled, reshaped, and sent wandering forever. And yet, exile does not mean insignificance. As strange as it sounds, these lonely planets may still harbor secrets far more extraordinary than anyone once imagined. At first glance, the idea of life on a rogue planet feels almost absurd. Life, as we instinctively understand it, is tied to sunlight photosynthesis, warmth, seasonal cycles, and stable climates shaped by a star. Strip all of that away, and what remains seems hostile, barren, and utterly lifeless. A rogue planet drifts through eternal night, its surface exposed to temperatures that plunge toward absolute zero. Oceans freeze solid, atmospheres collapse, and chemistry slows to a crawl. For decades, this image alone was enough to dismiss rogue planets as dead worlds. But science has a way of overturning assumptions, especially when those assumptions are built on limited examples. Life on Earth itself provides the first crack in that certainty. Long before plants covered the land or algae filled the seas, life thrived in darkness. Even today, entire ecosystems exist far from sunlight, buried beneath kilometers of ocean water or trapped beneath ice. Deep-sea hydrothermal vents, powered not by solar energy, but by geothermal heat from Earth's interior, support thriving communities of organisms. These ecosystems are fueled by chemistry rather than light, by reactions driven by heat, pressure, and minerals rising from the planet's core. If life can flourish there, the absence of a star may not be the death sentence we once imagined. Rogue planets, despite their cold exteriors, are not necessarily frozen solid from the inside out. Many retain significant internal heat left over from their formation, as well as heat generated by radioactive decay within their cores. If a rogue planet is massive enough, this internal warmth could persist for billions of years. Beneath a thick crust of ice, liquid water oceans may exist, dark, pressurized, and insulated from the vacuum of space above. These hidden seas would be invisible to the universe, sealed away beneath kilometers of ice, yet potentially stable for timescales long enough for life to emerge and evolve. A thick atmosphere could make this scenario even more plausible. Some rogue planets, particularly those comparable in size to gas giants or super-Earths, may retain dense atmospheres rich in hydrogen. Hydrogen is an exceptional insulator. Under the right conditions, such an atmosphere could trap heat so effectively that liquid water could exist on or beneath the surface, even without stellar input. In this case, a rogue planet would not be a frozen rock, but a warm, pressurized world wrapped in an invisible thermal blanket, drifting silently through space while remaining habitable on the inside. There is also the intriguing possibility of moons. If a rogue planet retains a large moon or several, the gravitational interaction between them could generate tidal heating. This is the same mechanism that keeps Jupiter's moon, Europa, geologically active and maintains a subsurface ocean beneath its icy shell. On a rogue planet, tidal forces could provide a steady source of energy, flexing the planet's interior and producing heat long after its ejection from a star system. In such a system, life would not rely on sunlight at all, but on the slow, rhythmic pull between two dark worlds, locked in an eternal gravitational dance. Of course, any life that evolves on a rogue planet would be profoundly alien. Without sunlight, there would be no plants, no vision as we know it, and no familiar ecosystems. Life would likely be microbial, adapted to extreme pressure, darkness, and isolation. Metabolism would be slow, conservation of energy critical. Evolution might proceed at a different pace entirely, shaped not by seasons or day-night cycles, but by geological rhythms and chemical gradients deep within the planet. Such life would never look outward toward the stars, because the stars would mean nothing to it. Yet this very isolation could offer a kind of stability rare on surface worlds. Without asteroid bombardments driven by stellar gravity, without stellar flares or radiation bursts, subsurface environments on rogue planets might remain undisturbed for immense stretches of time. On Earth, mass extinctions have repeatedly reset the evolutionary clock. On a rogue planet, life once established might persist in relative continuity, evolving slowly and steadily over billions of years. Paradoxically, a world without a star could offer one of the most stable environments life could ever experience. This forces scientists to confront a difficult question. If life can exist without stars, then how common might life be in the universe? Rogue planets could vastly expand the number of potentially habitable environments. Instead of life being confined to narrow habitable zones around stars, it could be scattered throughout the galaxy, hidden inside dark worlds we can barely detect. The universe might not be glowing with life, it might be quietly filled with it, tucked away in places we never thought to look. From a philosophical perspective, the idea is both humbling and unsettling. Life may not need warmth, light, or even a home star. It may arise wherever energy flows, and chemistry has time to experiment. Rogue planets represent the ultimate test of life's resilience, stripped of nearly everything we associate with habitability. If life can persist there, then the universe is far more fertile and far stranger than we ever imagined. And yet, for all their potential, these worlds remain silent. Any life they harbor would be trapped beneath ice and rock, sealed away from the cosmos. Rogue planets would never broadcast their presence through radio signals or atmospheric signatures easily visible from afar. Their life, if it exists, would be introspective, inward-facing, and unknowable. They remind us that the universe does not exist for our convenience, that some of its most profound stories may unfold entirely beyond our ability to witness them. If rogue planets are as numerous as scientists suspect, a natural question follows. Why haven't we seen them everywhere? The answer lies in their nature. Rogue planets do not shine. They emit no visible light, reflect no stellar glow, and drift through regions of space where darkness dominates. In astronomical terms, they are nearly perfect at hiding. Traditional planet hunting methods, those that rely on detecting dips in starlight or stellar wobbles, simply do not work when there is no host star involved. To find a rogue planet, astronomers must rely on indirect clues, fleeting moments where gravity briefly reveals what light cannot. The most powerful technique for detecting rogue planets is gravitational microlensing, a method rooted in Einstein's theory of general relativity. When a massive object passes in front of a distant star, its gravity bends and magnifies the star's light, acting like a natural cosmic lens. For a short time, sometimes hours, sometimes days, the background star appears brighter. If the lensing object is a planet, the signal is subtle and brief. If it's a rogue planet, there is no accompanying star to complicate the signature. The planet announces itself once and then vanishes back into darkness. Microlensing events are rare and unpredictable. Astronomers must monitor millions of stars continuously, hoping to catch these brief alignments by chance. Most of the time, nothing happens. But when a microlensing event does occur, it offers a tantalizing glimpse of an otherwise invisible world. From the shape and duration of the light curve, scientists can estimate the planet's mass and speed, even though the planet itself remains unseen. Each detection is like finding a footprint in the dark, evidence that something massive passed through, even if it left no lasting trace. Over the past decade, microlensing surveys have begun to uncover a surprising number of free-floating planetary mass objects. Some appear to be as massive as Jupiter, others closer to Earth in size. These findings suggest that rogue planets are not rare outliers, but a widespread population. Yet, microlensing has limitations. It tells us almost nothing about a planet's composition, atmosphere, or internal structure. It reveals existence, not character. To truly understand rogue planets, astronomers need new tools, new strategies, and a new way of thinking about planetary detection. This is where next-generation space telescopes come into play. Future missions are being designed with microlensing in mind, capable of monitoring vast regions of the galaxy with unprecedented precision. By observing from space, these telescopes avoid atmospheric interference and can detect far subtler signals than ground-based instruments. The goal is not just to find rogue planets, but to count them, to determine how common they are, how massive they tend to be, and how they are distributed throughout the Milky Way. Some rogue planets may also reveal themselves through heat rather than light. Young or massive rogue planets can emit faint infrared radiation as they slowly cool, glowing softly against the cold background of space. Infrared surveys have already identified isolated planetary mass objects in nearby star-forming regions, blurring the line between planets and failed stars. These detections suggest that rogue planets are not only numerous, but diverse, spanning a wide range of masses, temperatures, and formation histories. Even with these advances, most rogue planets will remain undetectable. They will pass silently between stars, never crossing the precise line of sight needed for microlensing, never glowing brightly enough to be seen in infrared surveys. This means that every rogue planet we detect likely represents many more we miss. Astronomers must rely on statistics, extrapolating from small samples to estimate a vast hidden population. It is a humbling reminder that our view of the galaxy is incomplete, shaped as much by what we cannot see as by what we can. There is something deeply poetic about this hunt. Astronomers spend their lives studying light, measuring it, dissecting it, following it across unimaginable distances. Rogue planets defy this approach. They force science to pay attention to absence, to distortion, to momentary anomalies. Finding them requires patience, persistence, and an acceptance that certainty may always remain just out of reach. In chasing rogue planets, astronomers are not just mapping objects, but learning how to study the unseen. The challenge of detection also shapes the kinds of questions scientists can ask. Without direct observations, discussions about rogue planet atmospheres, geology, lore, potential life remain largely theoretical. Yet theory is not guesswork. It is built on physics, chemistry, and comparisons to known worlds. Each new detection helps refine these models, narrowing the range of possibilities. Slowly, piece by piece, a clearer picture begins to emerge from the darkness. As detection methods improve, rogue planets may transition from curiosities to essential data points in planetary science. They offer a unique laboratory for studying planets stripped of stellar influence, allowing scientists to isolate internal processes that are often overshadowed by a star's presence. By comparing rogue planets to their star-bound counterparts, researchers can better understand how much a star truly shapes a planet's evolution and how much happens independently. Deep within a planet's interior, in this sense, rogue planets are not just difficult to find, they are difficult to conceptualize. They exist outside the frameworks that guided planetary science for generations. They do not fit neatly into diagrams of solar systems or habitable zones. They occupy the spaces between stars, the margins of models, the blind spots of observation. And yet, it is often at the margins where the most transformative discoveries are made. The hunt for rogue planets is still in its early stages, but it is already reshaping our understanding of what a galaxy contains. The Milky Way may not just be a collection of stars with planets attached, but a dynamic ecosystem filled with drifting worlds, each following its own lonely path. As detection techniques advance, the darkness between stars may slowly begin to give up its secret sand, reveal that it was never empty at all. If rogue planets truly exist in the numbers scientists now suspect, then the Milky Way is a fundamentally different place than we once believed. Our traditional image of the galaxy's stars as anchors, planets as companions, may be incomplete. Instead, the galaxy could be dominated by wandering worlds, drifting through its spiral arms in vast unseen currents. In sheer numbers alone, rogue planets may rival or even outnumber stars. This realization forces a shift in perspective. Stars may be the bright exceptions, while darkness, solitude, and planetary exile are the norm. This abundance reshapes how scientists think about planetary formation on a galactic scale. If planets are routinely ejected during system formation, then instability is not a failure of planetary systems, but a feature of them. The galaxy may be constantly recycling planets, creating them, scattering them, and redistributing them across interstellar space. Rogue planets become messengers of this process, carrying information about how violent, dynamic, and interconnected planetary systems truly are. There are also implications for the movement of material and, possibly, life through the galaxy. Rogue planets could act as cosmic couriers, transporting complex chemistry across vast distances. If microbial life ever arose on a planet before it was ejected, that life might survive deep underground, shielded from radiation and extreme cold. Over millions or billions of years, such a planet could drift near other star systems, raising provocative questions about natural panspermia and the long-distance exchange of biological potential. From a future human perspective, rogue planets represent both a challenge and an opportunity. Interstellar travel, as daunting as it is, may one day rely on intermediate waypoints places to harvest resources, study exotic environments, or shelter robotic explorers. A rogue planet passing relatively close to our solar system could become a temporary destination, a moving island in the cosmic ocean. Unlike stars, rogue planets do not emit deadly radiation or intense heat, making them strangely appealing targets for distant exploration. These worlds could also offer insights into planetary survival under extreme conditions. Studying rogue planets would help scientists understand how atmospheres evolve without stellar input, how geology proceeds in isolation, and how long internal heat can sustain activity. This knowledge feeds directly into our understanding of Earth's future as well. Billions of years from now, as the sun changes and eventually fades, Earth itself may begin to resemble a rogue world in slow transition. In that sense, rogue planets are not just alien, they are prophetic. Astrobiology, too, is permanently altered by their existence. If life can persist in darkness, fueled by internal energy rather than sunlight, then the universe's habitable real estate expands dramatically. Life may not cluster around stars like moths around flames, but instead exist quietly throughout the galaxy, hidden beneath ice and rock. The search for life may need to move beyond looking for atmospheric signatures and radio signals, toward a deeper understanding of planetary interiors and chemistry. There is also a philosophical weight to rogue planets that is difficult to ignore. These worlds are reminders that the universe does not guarantee belonging. Planets can be born into families and still be cast out. Stability can be temporary. Order can dissolve into chaos without warning. And yet, despite that, these planets endure. They continue to exist, to evolve, and perhaps even to harbor life, long after their connection to a star has been severed. In many ways, rogue planets reflect the galaxy's indifference in its generosity. It is indifferent in that it allows worlds to be expelled without purpose or ceremony. But it is generous in that it allows those worlds to persist, carrying complexity forward rather than erasing it. The universe does not waste what it creates. Even in exile, planets remain part of the cosmic story. As astronomical technology advances, rogue planets may move from the shadows into scientific focus. Future surveys could map their distribution, estimate their masses, and perhaps even identify nearby candidates for direct study. What now feels speculative may soon become measurable. Each new detection will refine our models, challenge assumptions, and deepen our appreciation for how little we truly know about the space between stars. It is possible that one day humanity will discover a rogue planet passing silently through the outskirts of our solar system, dark world gliding past, unnoticed for eons. Such an encounter would be a profound moment, a reminder that the galaxy is not static, but alive with motion. Our solar system itself is not isolated. It is part of a vast, shifting environment filled with travelers we are only beginning to recognize. In the grand narrative of the universe, rogue planets occupy a strange role. They are neither stars nor debris, neither failures nor successes. They are consequences, natural outcomes of a universe governed by gravity, motion, and chance. Their existence tells us that creation does not always produce neat results, and that complexity often emerges from disorder. For scientists, rogue planets are an invitation to think differently. They challenge long-held definitions, stretch detection methods to their limits, and demand new theoretical frameworks. For philosophers, they raise questions about belonging, isolation, and persistence. And for everyone else, they offer a powerful reminder that the universe is far stranger and far richer than our instincts suggest. Perhaps the most humbling realization is this: if trillions of rogue planets drift through the Milky Way, then the night sky we see is only a fraction of what exists. The stars shine brightly, but they do not tell the whole story. Between them and the cold and darkness, countless worlds move silently, each one a chapter written in gravity rather than light. Rogue planets are the galaxy's quiet majority worlds, without suns, without orbits, without witnesses. They roam endlessly, carrying the memory of violent beginnings and the possibility of hidden life. And as we begin to uncover their presence, they remind us that the universe is not built solely from what we can see, but from what drifts unseen, waiting patiently for us to learn how to notice.